So we are at a milestone that we've been really excited about for a long time. We're not, well, I should say we're pushing up on this milestone. We've about completed a major project that's taken years, right? We've got a few last puzzle pieces to fit together, but the majority of them are really fitting together already. So what we want to do is try to give us some background information of what the major project is, what are we trying to do, and then an overview of where we're at so far. So what we're trying to do is make sense of any universe. That's our starting point, right? In general, we want to eventually make sense of exactly the universe we have. But to start, let's just imagine that we didn't have a universe. Or imagine somehow we can conceive this domain. There's no universe. There's no properties in existence. So we're going to allow an infinite void filled with random noise. So there's waves going all through this void, the small waves to big waves, and they're intersecting and going past. But whatever occurs in this infinite void doesn't persist. It doesn't repeat. It's not there again when you look later at the same point. Okay? So there are no persistent elements, no persistent properties that are in this infinite random universe to point to. Most importantly, there are no bases, right? There are no units or sizes of anything that make any comparable sense. Okay, so you can't make sense of anything in this nonsense universe, the one that doesn't have any properties in it, in any way at all. It doesn't have any bases by which you can be making the comparisons or definitions. So, if we want to move from that infinite void that doesn't have any properties, that non-universe, to any universe, to get a universe out of it, we need to understand what's needed to be a universe. What are the basic minimal properties you have to have in order to persist? In order to have a property and then later still have that property. Okay? The simplest possible thing, just to exist in a persistent way. So you manifest same rules over and over and over, same actions over and over. One of the first things you would need is you would need those waves to come together in just the right way so that when they perform a loop, they're back in the position they were before at some point. So that things have to be persistently existing. So they have to be looping up somewhere, right? Things have to break up into pieces, and these waves have to force the domain to break up into pieces of different sizes perhaps, but they have to break up into pieces that are rotating about. And when that rotation is complete, it looks just like it did when it started the rotation, so it goes again. Okay, so the whole system has to divide, break up into a construction that's self-persistent. Literally the parts that we're breaking the system into become the logic that maintain the system. Okay, now first step is we need that infinite void to take on a finite distortion that wraps back on itself. Somewhere in the infinite void there's going to be a finite region. Now before this happens, before we get some sort of manifold that continues to balance itself, let's really focus on the fact that there are no quantum bits of any kind. There's no tick for time. There's no base unit for length. There's no unit of charge, right? There is no charge. There is no mass. These properties that we see persistently there in our universe don't exist at all in the infinite void. So what we're really after is a system that puts all the waves together just right, that breaks itself up internally just right, so that afterwards there are persistent bases playing off of each other. There's something we can point to and say, that base, we can label time. What's important is not the label. What's important is that time, that base of the partitioning system, is connected to the other bases. All of those bases come into existence by these waves coalescing and breaking up in a way that then self-perpetuate. So it needs to be a system, however it breaks up, that's invertible. So it's a very important. So it needs to be an invertible system. Okay, what does that mean? Its parts are coming together to turn the whole structure inside out and then continues in right side in and inside out, right? And this is where the cyclic nature comes from inverting the structure over and over. All the boundaries that come together are pushing against each other to twist the system inside out and does this over and over. Okay, So it needs to be invertible. And what sort of geometry? Well, the invertible condition itself restricts us geometrically in a very powerful way. Do you see why?
Something hyperbolic.
Yeah. Hyperbolic geometry is inherently invertible. Okay, so you don't have to specify the scale for this to work. You can get any hyperbolic universe, and that structure will be an invertible structure. So what do we mean by hyperbolic? We mean that the waves come together to form boundaries, and the boundaries have the characteristic shapes of the hyperbolic boundaries. Okay, for example, we start out with this conic structure. Imagine the cone continues this way and continues this way. This conic structure is the invertible essence of what's going on. Everything's getting flipped upside down, right? Twisted inside out. Okay, but this division structure, it's like a division boundary. You took all this fluid in this domain and you broke it apart so that this is the division boundary in the dead center. This is the center point of all the division construction, okay? But we're not going to separate, we're separating into a finite universe, a finite construction balanced against itself. It's not infinite. So the top sheet and the bottom sheet here that get separated have a gap between them. If it was infinite, if we were trying to make an infinite universe and put a hyperbolic structure to it, then the infinite hyperbolic structure wouldn't show a gap, okay? But if it's finite, you have a gap. And the smaller it is, the more finite your universe is, the bigger the gap. All right, so here's what I mean by the gap. Inside that bowl, there's this two-sheeted hyperboloid. So imagine everything is getting twisted up. We form another boundary here together with this one. These come together. We call it the two-sheeted hyperboloid. But at the same time, we get the one-sheeted hyperboloid. So these are surfaces, two-dimensional surfaces. Or imagine a bowl here and a bowl here that extends. And here, this whole surface here is one surface. So it's wrapping around, okay? This is simply just the way we hyperbolically divide in general. You can change what hyperbolic space we're talking about by squeezing these bowls closer and closer together to make a bigger and bigger hyperbolic structure. But this is just how hyperbolic structures divide. There's one other surface created here. Right? And imagine it comes out around here too. Okay, this is the torus or toroidal structure in our hyperbolic space. Okay, so this gives us an invertible construction. If you've achieved waves coming together so that the system itself is internally inverting hyperbolically, then you have a balanced hyperbolic structure. Fantastic. Where do we want to go from this to make sense of a universe? Well, first of all, what essences of a universe do you have just by wrapping waves together hyperbolically? What properties are invented right then?
Well, at that point, I would assume we would be looking for some type of smooth surface like a manifold.
Yeah, let's zoom out. If you zoom out enough, this whole structure collapses into small scale somewhere down in here, but we eventually get a finite universe with all of this conic structure on the inside. Okay, there's a finite reach in which all the actions on the inside are playing any role at all. Once you get out to that boundary, there's literally back to just noise out here. Everything out here is the random noise we started with. Okay, but inside that finite reach of that universe, we have a balanced construction. We have a division logic or a differential algebra. Okay, John Williamson helped me point that out. We're not really looking exactly for a division algebra, because we're not going infinite. We're looking for a differential algebra because we're going to have differentials in it. We're going to have base units of certain fixed sizes that are breaking up this projection. So if we think of the universe we create in our balance as the projection, then it gets a very special number attached to it. Okay? It becomes the reference, right? So in this balanced system of logic, the reference gets the number 1. All right, so we're projecting something into existence. We call that balance 1, that construction or projective construction 1. But then we have to note that the 1, when we zoom in, is being broken up more than one way. There are more than one kind of boundaries being formed in this balance on the inside, okay? Which means the one, the projection itself, is broken apart into 5 different kinds of actions. Or the one itself has 5 dimensions to it.
So those are, you can consider them basically subdivision surfaces or interpolation schemes. If it's,
Yeah.
So if it's physical, like in a way that we think you touch, whatever, that's a subdivision surface.
Yep.
That kind of gives it away. But an interpolation scheme would be more for anything that's distribution, like either of energy or time, something that has capacity.
Yep.
That's one way of thinking of it.
Yeah. So now we have a one, the projection, but there's 5 ones in a way. This one itself is breaking up 5 different ways. And that becomes the sense of the base in this projection. There's 5 bases, right? The projection breaks up 5 ways, so there are 5 independent ones that matter. The one is divided into this many pieces in one way, into a different number of pieces in a different way, and a different number of pieces in a third way, and a fourth and a fifth. So all 5 ways that the projection divides internally, all 5 infinitesimal units, or quantized units, become the 5 different bases of the balance. With me so far?
Yeah. In a coherent system.
Good word, coherent system. This structure by definition becomes a recursive coherent system, right? All the bases it invents, by the ways it breaks up, are coherently combined. They're coherently related. They have a logic that relates between them. And that coherently relates. What does that mean, coherently? Why do I keep saying that word? Coherently means that they all refer back to the one, the projection of the system, that they all have a one point, and they're all dividing up that one in different ways, but the way that they differ defines the logic of the structure. We're inherently talking about a balanced system too. It's not just invertible, it's balanced, of course, right? So that's an important feature. So we now have some clues, of course, in physics. Maybe I should keep that for now. That there are 5 modular bases in the real universe. Okay, we're imagining any possible universe here where we're allowing the scaling parameter in our hyperbolic structure to be anything, right? We didn't label this gap size here yet. But when you pick an actual gap size, then you've fixed your dynamics to a specific hyperbolic space. Okay. Well, in physics, there are 5 modular bases known as the Planck constants. Somehow have to relate to some hyperbolic structure. So let's write down the 5 different Planck constants. We've got the Planck time. We've got the Planck length. We've got the Planck charge. We've got the Planck mass. And we've got the Planck temperature. All right, so in our universe that we've observed using physics, we've got some constraints on the 5 different bases of the hyperbolic structure. This is a big advantage. It's a huge advantage. If you're looking for the internal structure that actually encodes our universe, the real universe, not just the first hypothetical possible one, then you really need a way to stipulate what scale are we using the hyperbolic structure on? What's the size of this gap, right? That determines the angles, that determines the way all of these boundaries fit together, what sizes they all are from that one gap size. All right, so we need to fit the boundaries of these 5 Planck coherent system bases to a hyperbolic structure. Let's start with the cone. This 2-dimensional surface in the middle of the whole structure is the charge boundary. Okay, and I mean it to be all the way the whole cone, not just where I wrote it. Okay, the mass gap separates the mass boundary. These 2 bowls, inverse and up, are both on the mass boundary. The torus is the space boundary, the base boundary we form when we make this. Okay, so we've taken care of length, is this what I meant by space, right? Charge, mass, and temperature is now, let's put it here. That boundary. So all of these boundaries are coming in together and balancing each other. If you removed the space boundary, notice this division boundary here and this division boundary have another balance boundary right between them. If you take a point here and a point there, there's always right between it another point that corresponds to the temperature boundary. Because it's a balance, it's put together by the division boundaries on both sides. Okay, so we have two kinds of boundaries. Well, we have 4 kinds of boundaries shown right here right now, but they break into 2 groups of things. Things that are being balanced into position, and the surface is being put together by something else, and ones that are being torn apart. Go ahead.
So temperature couldn't that also be seen as like a involution or whatever,
Of
inversion where mass has now used its charge and hit the space boundary?
Yeah, you know, you're good to notice that as you go zoom out, this space boundary gets almost invisible, but you still have the mass and temperature boundary riding both sides of the charge.
And space is like the, is in some ways going to be the arena of what is it's the transition state between one thing and another.
Okay. So, and remember, a torus is a
inversion of a
what kind of surface? Yeah, it's the inverse of a 4-dimensional hypersphere. Okay, so we have an internal bound here torus that's going to make you expect the outer structure, when we zoom all the way out, is a 4-dimensional hypersphere. I should stipulate right now what we're really imagining is a universe that's just one helium atom. The thing we're oversimplifying, the details we're missing still in this picture, is that we need each of these bases to modularly exist. They need to break up into a certain number of pieces, whatever that number is, but all of them have a number of pieces that they're modularly broken up in. And I didn't draw the breakup number of pieces. I did it as if it was continuous, smooth, each type of boundary, okay? So what we're needing now is a way to fix the Planck constants into quantized modular hyperbolic space. Time has a base of seconds, right? Length has a base of meters. Charge has a base of coulombs, mass has a base of kilograms, and temperature has a base of Kelvin. Now, this is an extremely important point that's very common to miss today, wildly common to miss. The second, the meter, the coulomb, the kilogram, and the Kelvin are not randomly picked bases. Okay, let's back up a step. When you look at an atom and you shine light in an atom and it emits a photon with a certain frequency, characteristically over and over and over, that wavelength, that frequency, is not random. It wasn't chosen by a human. It was observed. It's there as a fixed feature in reality. When we're breaking things up under a very fixed structural balance, the bases of that balance are the one that each is breaking up. Time breaks the projection up a certain way. And the one in time, when you talk about the one, and then talk about the way time breaks up one, we call that one seconds. Okay? It's a one of the projection broken up in the way time breaks it up. The thing we're calling time, we're making up the names of the bases, but in the structure, they're necessarily bases that play against each other in a logic. And we have to give it a name. Historically, everyone knows that the second didn't start out with that definition, right? So this is what's confusing the most, is say maybe the meter is the common one, right? You think the meter has a historic definition that started out in a kind of a useful, best thing they could go with. But eventually when we got more and more information in physics, we got more and more equations in physics. Things relate in a fixed with an equal sign way over and over in physics. Those equations taken collectively forced us to the basis that's most coherently supportive of all the equations in physics. The second is a base in physics. It's not picked by humans. It's discovered by humans, maybe other alien species somewhere else too, but they would discover the same base. They would discover all 5 bases. They'd probably pick completely different names for them, but they would have the same base. Okay. Those 5 bases are coherent. That's the second step, right? They're each not randomly picked. They're all each forced upon us by the rules of physics. And all of them talk together with each other, right? They're fixed in relationship to each other. All right, so what we want to do is figure out what kind of modular form in this hyperbolic structure each one of these bases takes on. In other words, how many pieces does the second divide into along the Planck time boundary? How many pieces does the meter, the one that we're projecting the whole system, divides 5 ways? So if I pick just the way that the meter divides, or just the way the length boundary divides this torus, if we just talk about the way that the torus divides up the projection, then there's going to be a number of quantum pieces that is doing it. Why do we know it's going to be a whole number, not infinity, not a partial number? Because we're starting with a quantized system that we assume is not infinite, it's finite. So in order for it to be modular, it has to be able to wrap against itself in a whole number of loops. It has to be in whole number loops. It can't be in fractions or irrational numbers. So there's an essence of the modularness here that includes whole numbers. There's other prescriptions for putting things together hyperbolically, lots of prescriptions that'll be irrational numbers, right? But they have to have closed form prescriptions to talk about how you're putting rational things together. All right, so when we look at the Planck constants, the things we've discovered from the constants of nature as our cutoffs in the bases of the coherent logic of physics, okay? These bases are these limits to our bases are extremely important because they're telling you the modular construction of each limit, okay? Here we have a string of digits, a power, and the base it's in reference to. That power right there is telling you the number of pieces these things are breaking up in. The modular structure is actually encoded in the number, right? So each of these things are modular forms. 5 completely different modular forms, and I really want people to practice not getting hung up on your previous thoughts of seconds and meters and coulombs and so on. Don't even think about what the name is, just give it the symbol or whatever, and think of it as a different base of the projection, a different way that the projection breaks up. Therefore, there has to be a logic between these bases, right? Because it's a manifold, it's closed, every action that's being formed is being countered, and there's a balance, and the whole thing inverts, and it persists. Here's our 5 bases. The green digits are new from our construction. The black digits are the ones we've gotten from physics so far. Now we're going to take this construction, and we're assuming hyperbolic space, which is pretty much forced on us in many ways, but we're assuming hyperbolic space that's modularly balanced and bounded exactly by the Planck constants. Okay. Next step, we need an equation for how this hyperbolic structure partitions. And we're calling this the hyperbolic Mobius boundary equation. 1 over x plus x, see the invertible structure here? Okay, plus x cubed over 2 pi equals, we're talking about a quaternion structure. I hope that for those who are familiar with quaternions, you look at this and see a quaternion right away, right? We're fitting together things like quaternion. Now I've been writing I to the negative pi over 2, but after talking to John Williamson and Arnie Ben at the Quizcycle group, he had a really fantastic suggestion. He said, why don't you, instead of saying I to the I and then telling people with words that these two are supposed to be just orthogonally arranged, instead we could say I to the j or k. Okay, remember I equals the square root of -1, but also j is another orthogonal square root of -1, and so is k. These are all orthogonal square roots of -1. Okay, so to make it obvious when you write this down that we're talking about 2 different orthogonal rotations in the plane, we're tracing out a corner, like down here, we're going 90 degrees that way, 90 degrees that way, and 90 degrees back. Okay, so to make that obvious that these two are different 90 degrees to each other, they're not just different 90 degrees, but they're 90 degrees to each other also. We read it like that. Great suggestion, John, thank you. And then we need a mass gap, which, bad handwriting, I don't like. So this is our hyperbolic structure referencing exactly this structure right here, okay? But if you pick a different size mass gap, then the structure scales slightly differently or maybe largely differently, okay? We're gonna pick a mass gap that's forced upon us by looking at the constants of nature, the rules in the constants of nature, and the equations of physics. And we're going to take this mass gap and just say, let's put in the Planck mass boundary as the mass gap for our hyperbolic structure. So this is it. This is our equation for how we partition all the parts of our hyperbolic balance. It's a fantastically simple and beautiful equation. It's just our hyperbolic balance pictured right here, but we've set this mass gap right here to represent the Planck mass. Right? So now our mass boundary is scaled by the actual mass gap we find in reality from measurements. Okay, this is a great start. Now, once we have that scaling parameter set up, we can then use this structure to find how all of the parts are breaking up and fitting together. Okay, just this equation to do all of that, which is really, really, really fantastic.
That's pretty freaking
It's
awesome.
really awesome. When we look at what the structure tells us, we get very specific partition numbers referencing this structure. Solutions to this equation. That's what I'm saying. So if we plug this equation in, right, you might in Wolfram Alpha have the right I to the I. I don't know if it has J automatically in there.
J gives kids something else. You can just do square root of -1.
Yep, you can write it like that too.
Now.
Perfect. So you get solutions, and I'm going to name the solutions in order how they pop up when I ask. And I'm going to get J1 is the first solution that you put this number into x, and x, then it satisfies this equation. Okay, and then there's J2 and J3 and J4. 4 solutions. 3 and 4, let me draw them here. If we were to graph these numbers, then J1 is real close to 0 on the real line, on the x-axis here. J2 is also on the x-axis, but further over, 3.66-ish. And then 3 and 4 are in the negative x direction, positive y for 3. And in a mirroring across the plane there, we get J4. So the x component of J3 is equal to the x component of J4. They're both negative and they have the same value. But the y component is opposite. They have the same string of digits, but this one's got a minus sign in front of it. Also, if we start from the origin, not from J1, but from the origin, and draw a line straight up to J3 or to J4, then we can talk about all 4 of these in polar coordinates. J1 and J2 are the same as they were because they're on the axis, they don't have any angle, right? But right here, this is J theta, the angle from the axis, the x-axis, to get to J3. And if you go this way to J4, then it's negative J theta. Also, if we go from the origin and get the radial length to J3, not just the x and y position, but the radial length, that's Jr. It's also Jr here. Same thing. Okay, so we have 6 numbers that represent this construction. Jr and J theta are just the polar coordinate way of representing the same set here. Okay, so it's really just the 4 solutions, but you can talk about those 4 solutions in Cartesian coordinates or you can talk about it in polar coordinates. Both can be useful for different things. All right. Also, just to make it absolutely clear, J3 is equal to Jr times E times J theta, E to the J theta. And J4 is equal to Jr times E to the minus J theta. Oops, I need an I. There.
Well, that's looking a little familiar. The natural base of logarithms as a
Yeah,
function.
yeah. But this is just pictorial. I mean, what I showed you pictorially is the same thing here. But for those who are familiar, there we go. So these numbers, we made up the symbol for it. It's acrylic symbol. But these are the solutions to this partition construction of the hyperbolic Mobius partitioning. Okay, it's a Cyrillic number.
Yeah, Russian.
From Russian. Yeah, the sound is zh. Yeah. Okay. So with me so far, we got a quaternion structure of our hyperbolic space that's dividing up exactly under this arrangement. The gap in that arrangement is set by the Planck mass, And now we want to use this structure, the implied structure of exactly this, which fixes the scale at all the interactions, to the constants of nature. We want to see, can we talk about partial sets of what's going on inside the system? So imagine you've zoomed in on a certain part of the system that's breaking up on one boundary and another boundary, and they're doing an action together. Can we reference that action specifically, right? Do the constants of nature have anything to do with that structure, or is it just the Planck mass that fits? The rest don't. That's what we're really after. So to make sense of that, we need to look at the balance of these projective solutions, meaning if I take the first one and add it to the second one, that's a one-dimensional number, that's a one-dimensional number. And we're going to add a two-dimensional number and another two-dimensional number. We add all of our solutions together for this partition construction to get what happens when you have all of them summed, and we get 0. Fantastic start, fantastic start. The balance we needed to begin with. The thing partitions, but if we take all the roll of those partitions, it's balanced. Great. But what now? So this is the sum. So when we're taking many part systems, you can take the sums and find out interesting things. You can take the product to find out interesting things. You can take the quadrants to find out what you're quadranting up, right? What shape is being divided up. Let's first take the product. J1 times J2 times J3 times J4. So instead of adding them, we multiply them, and we get 2 pi.
Oh.
That's beautiful and penetratable for everyone, I imagine. We get a circle. The product of these partitions is a circle. Very modular form structure suggestively already. Now let's take the quadrants. This is a standard way of just looking at the structure of your algebraic system. And now, the quadrants of these solutions is -4 pi. It's a projected sphere. Fantastic. So that's the whole system. In fact, this equation is best looked at in complete form with these equations, right? It's like the complete way of looking at what this structure is doing. But what if you want the partial sets of what's going on too? You don't want to just stand back and say, oh, I see a sphere where all the parts are combining together, you get a rotation, and it's projecting as a sphere and a balance. Great, but inside that system, inside that balance of algebraic geometry, if I want to point to a specific part in the balance, okay, which ones are available to us just from the algebra here? Well, notice these numbers, 0, 2 pi, 4 pi, these are numbers you can write down on a single dimensional, like a number line, okay? It's really easy for us to say, that's a thing because it's, oh, measurement, got it, it's a one-dimensional measure. What we want is to look at the partial sets of this construction that also give us one-dimensional numbers, outputs. All right, it's helpful, I'll put this chart back up. J1, J2, and then we'll refer to the numbers themselves on the screen real quick. It's helpful to remember what dimensions each of these numbers represent. This is always a one-dimensional, two-dimensional, and two-dimensional. So let's look on the screen real quick to see what I mean. Right here. J1 is a string of digits, but there's no second dimension. It's not a complex structure. It's a one-dimensional number. So is J2, but 3 and 4 are both two-dimensional numbers. They have an x and a y component. Okay. R and theta one-dimensional, but 1, 2, 3, 4 we're going to stick with. So what we want to do is ask what partial sets that are plural sets of things, so not single things but double things and triple things, can I take from this system that give us outputs that are one-dimensional claims? Does that make sense as a question? Okay, so let's take J1, let's go through a couple of them. Let's start from the top line here. We got 1 plus 2. Does that count?
Yeah.
Yes, that one does count. How about J1 plus J3?
No.
No, why not?
It's a one-dimensional number combined with a two-dimensional number.
Which doesn't collapse back to a one-dimensional number, so no, that one's not a partial set that we care about. How about, let's move 1 plus J4? Nope, for the same reason. And how about J2 plus J3?
Nope, still a one-dimensional.
Good.
Two-dimensional.
Also 2 plus 3 or 4? That's
Nope.
same problem. All right, how about 3 plus 4?
Yes.
Good, that one works.
They're both
All right,
two-dimensional.
I think it makes sense. I don't have to go through them all, but you go through every iteration of combinations here, and we're only, so far, we're only doing pairs. Now we have to do iterations of triplets. Okay, let's do that. Which combinations, this may be a faster way to ask, which combinations of this first set of 4 can you take 3 of and get a one-dimensional output?
Well, as long as you have 3 and 4 will collapse down to a one-dimensional.
Perfect. Perfect. If we're picking 3 things, if I pick these 2, it doesn't matter which one of these I pick, it wouldn't work, right? Pick 1, 2, and then pick that one. Nope, doesn't work, because these become one-dimensional and then are two-dimensional. But if I pick both of these together and one of these, either one, it will work, because these 2 added together becomes a real number. And then you can add that to it or that to it, doesn't matter, it still stays real. Okay, or by real I mean it's on the number line now. It's one-dimensional. Okay, so that's our 2 sets and our 3 sets. And to be extra clear here, we're also including.
So basically, yeah, totally imaginary fields and the totally real fields.
Yeah. This equation too, the opposite is also true, right? So we're going to take the 2 sets of the minus signs also. So I'm not going to include that for every time just for brevity, but remember, whenever we're writing these things, we care about the positive and negative versions of the summations of the collections. Okay, so in general, there's a very small set. It's not a very large number. There's a small set of partial collections that are plural of our partition parameters that give us outputs that we're interested in. Okay, things that we could assign to a measurement and make sense of. All right, that's the first row. The second row, we could work through the same thing. When you multiply these 2 together, it's still real, that's fine. These 2, nope. These 2, yep. Right, and you do sets of 3s and sets of 2s. So since we're only maximizing the sets of 4, and this is the sets of 4 relations already, the sets of 2s and 3s, this is kind of a small set. That small set is what we want to check against for our partition construction for every constant of nature in the book. So what we're claiming here is that the simplest possible way to make any universe is to make a hyperbolic universe. Okay? And then there's an argument of scale. Which exact scaling parameter in your hyperbolic space you're going with for the universe you're talking about? We're picking the scaling parameter that was given to us by measurements in physics, the Planck mass. Okay? And then we're going to take the construction that comes out of that and look at all the partial parts of that construction that will be in the balance. So the way this picture breaks up, we haven't encoded the modularness, the quantized number of pieces yet, because we're after that image, right? But that's the logic of what we're after. All the partial plural sets of this simple hyperbolic construction. Fantastic, okay. When we take every single constant of nature listed in the coherent system of units, using exactly only the bases that are defined by as the coherent system of units, which, by the way, the coherent system of units, all of those bases, the definition keeps changing out at further digits as we get better and better measurements, but the definition of the meter is changing. The definition of the second is changing. The definition of each of these bases changes as we get more data points to change it, because the definition of the meter comes directly from the constants of nature. Directly from measurements. This is not picked by any human. It's not a standard that we're all deciding to go with. This is forced upon us by the logic of physics. It's a very important thing to note. When we do this, the first thing I want us to look at is that this partition construction, this list of the constants of nature, transcribed in terms of our hyperbolic partitioning structure, can give us insights into what each of the different actions in that structure are doing, what they're geometrically and algebraically doing, what logic they maintain, what geometry they hold to do that logic. Great. So let's first, instead of looking at any specific one in full detail, let's first just notice this column here is all using J1 minus J2, one of our possible partial sets in our whole construction, right? J1 minus J2, every single one all the way down here, then we get J1 plus J2, more J1 minus J2s all the way down, and we get 3s plus 4s. So this column is a sum or minus of 2 of our J's, okay? It's a 2 set. This column is 3 set, right? 3 different J's put together, all the way down. The whole column is just a 3 set. So what we're doing is we're taking the 2 sets and 3 sets of our partial construction and trying to look for which constant of nature matches that part, okay? This is 2 sets of the bottom equation, right? The squared ones, or the quadrants one, and then 3 sets of the quadrants one. I mean, I'm hoping you're at least noticing that there is a pattern to be seen here. Now, let's try to help. If you haven't ever seen this before, what are we even saying? We're saying the speed of light, for example, is equal to the Planck length divided by the Planck time, our 2 bases intersecting. And on the right-hand side, the shape that's balancing that comes from the square root of the Giesking manifold, the Giesking constant, okay? We're saying the Giesking constant itself is responsible for the speed of light. Not just the Giesking constant, but also the way that we're breaking up to make that balance, and the boundaries in which it's moving on. The Planck length is a literal boundary in our construction, and the Planck time is a literal boundary, and the way that they relate gives us the speed of light, which is really interesting because the speed of light becomes our fastest possible velocity, right? And it rides on the smallest possible manifold.
Pretty cool.
That's pretty cool. In fact, it even kind of intuitively starts to make a little bit of sense. Why would it be the fastest possible speed? Because it's riding along the smallest possible boundary in the structure, which happens to be the smallest possible manifold. That's really nice insight, okay?
Also square root.
Mm-hmm. Yeah, it's dividing it. 1/2 power, yeah. Let's back out. Let's look at the left half here. All right. So we can express in terms of J theta and J r also, remember? Let's look at J theta first. This, if you put in the value of the Planck length, square it, put in the value of the Planck mass, divide that by the value of the Planck time and the electron mass, times the whole thing by pi, and then times it by this. This is the square root of zeta of 2, pi squared over 6, okay, times by J theta squared. So 2 of our rotations on our inversion boundary. The inversion boundary has this symbol because it's representing the internal structure of our projection. Okay, it's the hyperbolic internal structure, so the x through the middle. Yeah, and that's unique to all of these. If you notice, every single one has the same inversion boundary we're talking about. So this partition structure has an external expression and an internal expression. They're both taken together to make the constant, okay? But if you notice, we get, I should have finished where I was going. When you do that, when you plug in these numbers, you get the value of that constant with the right dimensions.
Yep.
You get the dimensions and the value within the error bars. And that's how we find it, of course, right? But that's the phenomenal thing. We're able to predict from this partition structure this constant of nature. And then this constant of nature. What's the difference? This one just had a 2 in front.
Yeah.
All right, and then this constant of nature, oh, it's a 1/2 instead. And this one's a 1/2 also, but instead of the electron mass becomes a proton mass. Spits out the exact right number. Not like kind of close. When we're talking about exact right, we're error bars with codata. You list your error bars of a certain size. That's how much you're confident with somewhere in here. Of course, that confidence range, it could be outside of your error bars, but the further out, the less confident you are it matches the number. What scaling is cut off? 5 sigma. 5 times bigger than the error bars. If you're 5 times outside of the error bars, you're wrong, right? That's how we know for sure. Now it's thrown out. It doesn't satisfactorily explain the data. Of course, most scientists are very uncomfortable with even close to 5. Like 4 would still be very suspicious. 3, okay. 2, okay. 1, of course, okay. That's what you listed. But why, in most experiments, you don't have the issue of the definition of the bases in question, right? In most experiments, if someone reports error bars of 1, you probably want to stick within 1, maybe 1.5. But when you're arguing over what the definition of the meter is and the second is out of those last digits, then you kind of have to allow a little more swinging. So it's common for CoData to swing when they update their numbers, 2 or 3. The last time they had one that swung out to 3.5 different than the one before. So that gives you an idea of how much ignorance we have on the last digits of things in science right now. But definitely want to be within 5, and all of ours, I think the biggest one we have is 3.5, just like their last swing. So these give us the actual outputs of the measured constants of nature. Okay? These algebraic relationships in the hyperbolic geometry give us these action outputs that are exact, not just exact digits and power, but the exact expression in units. Okay? And it's very important that it's in the coherent system of units. This doesn't work in feet. It never would work in feet. Feet are not a coherent system of units. The meter is the coherent system of units. Okay. Here is another example. See, the second and the electron volt are here in the constant. The second plays a role. The second, the 1 second. Okay. Does there again too. Still, the right-hand sides, this whole column so far, they're all exactly the same.
I mean, that's
oh,
a very
exactly the same.
That I haven't seen anywhere else.
Yeah, and then we get, 2 more at the end. Instead of Zeta 2, it's Zeta 3. Really, really, really nice collection we got going here. Now, I imagine most people aren't necessarily familiar or have memorized all the different details of all the constants. So we've got the symbols. You have to look at the numbers to make sure I'm telling the truth there, right? But the pattern is what we're trying to highlight right now. And if you get excited about it, you should crunch the numbers and see that it does give the exact thing. I'll post it too, save you a lot of time. Then we jump down. The pattern changes here at this conjunction here. And now we get e to the negative Euler-Mascheroni constant. Shows up in, what does that number relate to? Should we say or just draw?
Probably draw it.
Okay.
Because honestly, I don't remember, at least in this context. Euler's number, and then it's Euler's gamma.
When we talk about the hyperbolic logarithm is a simple graph. Y equals 1 over x. Pretty simple. It's our first step in here. Okay. Y equals 1 over x. If we draw this side over here, something like that. It keeps getting closer and closer and closer as we go out. All right. That's the smooth, hand-drawn version of the smooth curve y equals 1 over x. You can talk about this curve in the calculus way, where you're going to strip it up instead. Okay. So instead of, there's one limit. The strips could be infinitely small, and then you make this curve. Or you can take the step size, let's see, that's 1 and 1. You can put a square box in here, we get 1 unit square. And now we can step out another 1 step, get up here, and it's actually now at 1/2. And then if you go out another step, it's going to be at 1/3, and then 1/4, and so on. Okay, so it gives us the series of all the 1/2, 1/3, 1/4, and so on, right? From all these different steps. Then we draw in steps here. We got, I could make it 1, and then, so we can, instead of looking at the smooth curve, we can look at the quantized staircase that fits the curve. Now, what's the step in the staircase? 1. Okay, you could slide that back to 0 to get the smooth one, but you're also looking at the unitary limit of the hyperbolic logarithm. Step size 1 is the unitary limit. Well, if we start from here and we add up all the area of these steps all the way out, okay, we're going to get a certain value for the area under the steps. If we take the area under the smooth curve, so we're basically taking the curve and looking at it in a unitary step size and a 0 step size, and we're taking the difference between the areas of that way of breaking it up unitary or breaking it up with 0 steps. Okay, and that difference, that difference equals the Euler-Mascheroni constant. Okay, so the Euler-Mascheroni constant is intrinsically related, directly related to the hyperbolic logarithm, and it's related to the hyperbolic logarithm being broken up in two different ways, smoothly and stepwise. Okay.
Now, isn't the area under the curve Euler's number? Doesn't that add up to E technically if we were to go?
Oh, there is an E thing directly related here. If we, well, when we start at 1, we have a box of 1 area already that we've passed, right? And so this is a 1 by 1 or a 1 square area, right? Now, if we want to ask, how far do we have to go under the curve, not using the steps now, so just taking the smooth curve, and we want to take the same amount of paint that it takes to cover 1 square area and paint it in here. Well, you have to go further than to 2, right? You'll have to go past 2 because you missed this part, and you have to now put that down here somewhere. So somewhere over here is where you'd have to go to get now another square unit. So our second square unit comes out to here, and the value here is E, Euler's number. And if you could do it again, the next square area, somewhere out here, E squared, and then E cubed, and E to the 4th. So E has a unitary square relationship to the hyperbolic logarithm, two-dimensional one. It's two-dimensionally related to the hyperbolic logarithm. All right, so the zeta function, zeta of 1 plus x plus zeta of 1 minus x, so that's reflective, put them together, divided by 2. You get the average as we approach 0 in the zeta function itself goes to the Euler-Mascheroni constant. So it's intrinsically related to the zeta function, right? It's also intrinsically related to the gamma function. You just flip it over, but 1 over x there, and don't have the 2. Now we have 1 over gamma of 1 plus x minus 1 over gamma of 1 minus x, the reflection. And that, as we approach 0, in that structure, goes to 2 times Euler-Mascheroni. Perhaps another really interesting one, the ones related to the primes. These two both relate to, here's 6 over e to the Euler-Mascheroni, in the primes themselves. Times by what? 4 pi over gamma of 5, which is 24, and then squared. So this one's even simpler in its relation. E to the Euler-Mascheroni is just directly 1 over log of prime n, so all sets of primes. We're going to go from n equals, from 1 to n. And as we count up, as we keep adding more and more primes, and we take the product of 1 over 1 minus the first prime, 1 over 1 minus the second prime, and keep going, multiply them together, then that structure also goes to e to the Euler-Mascheroni constant.
But that, we just saw like a 6 in the Euler's number to the Euler-Mascheroni.
Oh yeah, this 6 over e to the Euler-Mascheroni, let's go back.
It looked like it was flipped.
Yeah, in fact, here, yeah, this was 1 over 6 times e to the Euler-Mascheroni if you want to put it on the bottom, but let's back out real quick and look at another one that's related more exactly to that, right here. All of these. Same exact structure in the primes, okay, which is part of the hyperbolic structure we're talking about. Now, the mystery, of course, in the hyperbolic space is why is there a specific scale picked? If you had the logic for why that specific scale was there, then the hyperbolic parameters would make more sense. Okay, where do we want to go from here? The major insight, now we're not done with this pattern. We're still trying to fit the best pieces. The most troublesome ones are the ones that have the smallest amount of significant digits. So your confidence is the most low on them, and they usually also spit out more possible things that could be. So there's a lot of arguing and debating over which ones best fit the parameter, fit the patterns. But you can tell when we get some set, you can definitely tell we've got a coherent pattern going here, right? Mm-hmm. We can try to interpret all the parts of it, but the stage we're at right now and almost finished with is trying to just take all the constants of nature and interpret them in terms of partial sets of our hyperbolic partition construction, okay? Find out which piece of the hyperbolic partitioning is this constant referencing. So we have to go through Wolfram Alpha. It's a big, long search over and over, and it's quite fun, actually, to be searching for a way to interpret a constant of nature.
You learn a lot.
You learn a lot.
You learn about it. I mean, I've been basically reverse learning mathematics, and then with actually trying to learn mathematics, learning how to code and everything like that. It's just the more you do it, And especially when you do stumble across something, and like, it might not be the ultimate answer. You're like, I've never seen something like that. And occasionally you come across some gems.
Yeah, and when you spend all your time looking for the answers that fit, you have to keep in mind, maybe it's not right yet, but it fits. If you're restricting your attention to the things that could be right, you're much more likely to see the path of the things that are right.
It helps when
It really helps. Yeah. All right, so let's do a little bit on how we're partitioning all this structure. What's the general rule? We're using the universal binomial factorization equation, which just means that we're taking the insight from this to say everything that's being balanced in the structure is being balanced by being broken up into an external expression and an internal expression, okay? Those things balance against each other in the way everything fits together, and whenever you point to that part of the system, you get that action. That's the action that's being tied together under that logic there. So the way we represent this, say there's a primary action on a primary set of boundaries, and then or external. Let me call it external now. Yeah, I think it's easier to see. So we have an external action on an external set of boundaries, and then the internal part is going to be under binomial construction with the external part. So 1 plus some internal action on an internal set of boundaries, but the internal set of boundaries, of course, in the structure are fixed. It's the same system for the whole thing. So when things turn around on the inside here, it's always the same. So those are fixed.
So should we note what that boundary condition is?
Yep. So that symbol, where you're writing like this, is literally equal to the Planck length times by the Planck mass divided by the Planck charge squared.
So if you actually plug that into Wolfram Alpha, basically it'll spit out 1 ampere. So that's approximately 10 to the negative 7, which when we look a little bit more closely, because we want to maintain coherence, it actually ends up being 9.99999999999 something.
It's real close to 10 to the negative 7, but not exact. It's got it on the 7th digit there. It's off a little bit.
9.99991.
No, it's really a figure complex thing.
9.9999199973622.
You got to memorize? Good.
Yep, nope,
Great. All right, so of course you can solve for it yourself easily when you look up our values of these and put them together and find it, right? But the point is to keep the picture in our head that the construction is balancing several different sets of actions exactly this way. Every single one is following that. Now, the internal action has to happen on one of the partial sets of our partition construction. One of those partitionings have to be attached to the internal action, and the external action is going to have partitions too. The sets available outside are, well, you can have no je, like you could have a 1 or something, but no je. But if there's jes, there's je1, it could be je1 squared, it could be je1 cubed. Oh, it's really hard to do that and say it at the same time, and so on. Or pairs, like je1 and je2, je1 squared, je2 squared, or even like je1 and je2 squared, all right, or je1 squared and je2, different sets like that. But 1s and 2s are on the outside, the external part, and the internal part is the whole possible sets of plural partial sets. Okay, that's the search space. So when we get a constant of nature, we go to CoData, we get the best known value. Maybe we look up even more to see if there's any new measurements because they're pretty behind on their update. But in general, we use the CoData information, and you write down the string of digits, the power, the symbol, and the name, right? But then also the dimensions that it's in. So we would write down, I'll do higher than that. For the speed of light, our symbol is c, and they give us 2.99792.458. And I'm going to put this little box right here to see they define it as exact, times 10 to the 8 meters per second. That's the input data. That's the thing we're trying to make sense of in terms of hyperbolic partitions. Okay, and this is the equation that we make sense of it with. Okay, it's going to be an expression in this balance somewhere, and this is how we tease apart the expression for each individual constant. So we would write down this number, power, and set it equal to some action that's external. We haven't solved, we're going to solve for it. And we write down the boundaries by looking at the dimensions of the reported constant and say meters per second. Okay, meters has a limiting boundary of the Planck length, and seconds has a limiting boundary of the Planck time. All right, so the bounds of these dimensions are going to give us insight about what the action on those bounds cause this famously known constant. Well, it turns out in this case, for the speed of light, that the external action is 1. So I don't really need to write it. I can write it even shorter. And then we need to, once we've solved for the primary or external action, we can then now, because then we now have digits that extend further, we can now look for 1 plus some, that's what we're going to solve for, some internal action on the internal boundaries. Okay, so since we know the value for this, and we know the value for that, and this, we can now solve for a number for that. Once we have this number, we have to search for it against all the possible partial sets in our hyperbolic construction. So we say, we take this x, whatever number it pops out as, and we have to set it equal to, start with, say, je r times what? Find out what that is. Maybe if it's nothing interesting, throw it out. And then you ask je r squared, and ask je r cubed. And you keep going through the je r's. Then you have to ask je theta, and je theta squared, and je theta cubed, and so on. And then we have to do our je 1 plus je 2. We have to ask je 1 minus je 2. We go through the whole same set of possible partial connections in our hyperbolic structure to see if any of them pop out interesting answers. And then you don't know for sure which one's right. What you're looking for is, well, if there's only one interesting answer, your confidence must be that. But if there's, say, 4 things that fit the data, depends on how many significant digits you have, how many you're likely to get, right? But the more digits, the more it constrains it. And the constants of nature are the things we have the most digits in measurement of. Some of them, a handful of them, are pretty kind of small, but the majority of them are quite out there, right? Way past what your senses can perceive. All right, so using this prescription, you have to make a table of all the possible subsets, right? Check it against that whole table of subsets, and then report the interesting answers. Okay, you're not going to report it as the final truth. You're going to keep a list of possible ones if there's more than one, right? But as you go through the whole set of things, you might find, oh, there's 3 possible ones for this right-hand side, and this other constant of nature has very similar left-hand side, and it has this one of the same possible answers. Okay, we can group them up and start to put together a story of how all these pieces are exchanging together, how they're all fitting together, how they're dynamically connected. Great. In fact, what we're doing then is resolving the inner details of the manifold, of the quantized manifold structure fitting to a specific scale of hyperbolic construction. That's what we're doing. We're trying to get the picture of that, yeah.
Is the boundary 10 to the 8?
This is 10.
Oh, that's speed of light. It's raised.
No. I'm saying the calculation of that LP, MP.
Yes.
MP squared.
Yeah, it's 10 to the negative 8. Yeah.
It's actually
because
a little squiggle
because 9.99 times 10 to the negative 8 is very close to 1 times 10 to the negative 7.
All right.
Yeah. That's a really good thing to note, by the way. The number of digits in the information given is extremely important to pay attention to. Right?
See, just to highlight, for like the speed of light here right now, the Planck units get the first 5 significant digits head on there. Mm-hmm. So since we only know the speed of light to 9 significant digits, basically you only need 4. So the 10 to the negative 7, the 10 to the negative 8, that tiny fluctuation won't really make a difference. In that case, but in if you're dealing with 12, 13, 14 significant digits, it makes a big difference.
Yeah, in fact, some of our recent work has been centered exactly around that. I had been using 10 to the negative 7 as shorthand to type because it's much faster than typing all that every time. And most of the constants don't get all the way out to the 14th digit, right? They're shorter, they're truncated before that. So the difference between this and that wouldn't show up.
And there's a difference if you use
But some of them do.
If you use the ones and you just cut off the green, the predicted values, and just use the certain values, you still get a value 9.99950324255.
Yeah.
747 642.
That's a great point. Let's take a little sidetrack here to ask, how did we get the numbers we have? Like, where did the rest of the green digits come from? And why are we using those? Because nobody else has those, right?
Oh, and somebody might want to reconstruct them to make sure that they come up with the same thing.
Yeah. Well, let me tell them how I did it so they have an option. Okay, so let's look all the way over here. We took the existing values of the Planck constants, which are found by comparing the constants in nature, right? You can see they're directly in the speed of light. So if you found another one that has the Planck length in it, you can find the Planck time just by relating it there. All right, so we took them and we assumed that they represent modular structures, right? In fact, the Planck temperature, let's go with Planck mass. No, let's start out with Planck time. So the Planck time's got this string of digits, only there we knew, and it has 10 to the negative 44 in the base that it's breaking up, okay? So we're going to say that it has to fit against itself. All 5 of them have to fit against themselves and the other ones, but we'll look at its self-restriction right now, and say it's going to be a rotation of some sort, a hyperbolic action that's rotated and fit into its own modular form. How many modular pieces does this one have to have? 44. This exclamation point n, the red n represents 5 here. So this is the derangements of 5 things.
The exclamation point when it's before the object
if it's
is a derangement.
If it's after, then it's a factorial.
It's factorial. And then for anybody who doesn't know what the derangement is, derangement is a permutation where the original position is not allowed to be repeated.
Every piece has to move.
Yep.
Nobody gets to just sit there and do nothing, which is kind of perfect for what we're talking about here. So the bottom of our structure is a derangement structure. Okay, it's a modularly deranged structure that has a hyperbolic action to it. Now, why do we pick this hyperbolic action? This hyperbolic action is what popped out from Wolfram Alpha when we searched. We plug in the actual known value for this rotation here. We plug in that, and then search against it to see which action at all, but you would prefer a nice hyperbolic one, to describe that fitting together, okay? And then we run with it. We find this one is a hyperbolic simple description, and we say, all right, let's treat that action as the action that's fitting the time boundary together. What?
Saying that somebody's modularly deranged sounds like something from a horror movie.
We're saying that the universe, by definition, must be modularly deranged. Yeah, it does. It does. Okay, so, and we do the same thing for the Planck length, right? The Planck length has 35 modular pieces that it has to be balancing itself against. So we put 35, that's a 7 times 5. I use the colors because I'm trying to make it very easy for my eyes to pull out wherever the 5s and 7s come from, because there's 5 bases, and then the very first step, once you get some circle in there, the very next step of construction would be a scale of 7 break in the bases.
I literally just grokked that right now.
Which part?
Because I've done the equations, I've heard the things. Now I'm seeing literally the 7 right there.
Yeah. Good, you're good. So this is the base boundary, this is the charge boundary, this is the mass boundary, and this is the temperature boundary. And each one has a different number of modular pieces it's breaking into, but they're all breaking up the external reference, the one. Okay? They're all talking about the same story of projection, but they're the individual pieces of the projection. And they all live on quite different scales. If you notice, the scaling comes from the modular number, right? Okay, so that's if you want to try to come up with a different construction, you would need a set of modular forms to justify the rest of the string of digits. So this is where the rest of the string of digits comes from in our case. And we're saying that we're balancing these 5 actions together all the time. You can take 2 of those and 1 of these and divide it by 3 of those in whatever cases. There's many different combinations, but this is the balance that's persisting all the time. So here's a picture of the balances. Let's go down to, here's the first one, time. It's wrapping, if it was the only one that was, if the other ones weren't also with it, it would wrap a domain exactly like this. You see this figure 8-ness, but like a double figure 8? In fact, if you take this is just looking straight down on this one, so 2 different views of the same thing. Okay, but you can see it's twisting the domain up in a very beautiful but symmetric way. If we take the same picture though, and imagine slicing down the middle here, and taking, say, 2 of these, the opposite ones, and turning them inside out.
Yeah.
Okay, we just separate it from that one and plop them down that way. Then it looks a lot like this one. Okay, let's do that again. Let's say we got rid of these 2 and push them down. We turn into this one. Now let's start from this one and cut it down the middle and say, which one do I want to push? Let's say we'll push this one down. And now it looks like that one. Right? This one's much more complicated. In fact, the features of this one worth mentioning is that one side is really smooth on the plane there, and the other side is very complex. It's kind of like a little...
charge boundary?
Yeah, charge boundary.
Okay.
It looks like a butterfly. Now these are modular. Imagine you got a flat sheet, and we've twisted them up in the way that modular form twists things up. But none of these things actually exist by themselves. They're all then fit together, right? It's just trying to pull them apart. What did you ask?
That third one down there is charge boundary?
Just charge boundary, yep. Charge, mass, and then temperature. All right, so you're kind of with me so far, what we're doing? We got the...
Can I ask a question about your universal binomial factorization? I've heard this expressed as primary actions and also as exterior-interior actions. You want to speak a little bit on...
originally, I used to call this primary action, primary boundaries, and then terminal actions and terminal boundaries. I think it's going to be easier for people to see. Well, first of all, I started from complete ignorance and tried to work my way to clarity. I think it's more clear to say outside and inside, or external and internal.
Okay, so you don't, and because terminal would sort of maybe give a, well, it gives an indication of series.
Ends, it sounds like, yeah. And that's why I'm moving away from terminal. I think internal, external sounds easier to understand and more accurate.
And so really then you're talking about, like I was saying, the information neighborhood interaction across the space boundary where a prescription comes in, information goes out as temperature.
Yep.
And the feedback.
This is the local neighborhood, how things are twisted up. This is the external expression of that neighborhood to everybody else.
Yeah.
Yep. All right, let's look at one of my favorite columns here. This is absolutely phenomenally beautiful how this pattern manifests here. Let's just look at it real quick first, and then we'll talk about it. We got a whole column of constants, which is 36 constants out of the 288. That's 1/8 of the constants. They're just in this one column. All of them have r squared, right? And so they're all fit. That's why they're in the column together, because there's r squareds, okay? But you also notice that they have a lot more in common than just being all r squareds. The top, yeah, if we look at the right-hand side first, over here we have 1/2 times the real part of the infinite power tower of I. What would that mean?
Sounds kind of like a spiral.
Like a spiral. You rotate, and then you rotate, and you rotate, and you keep rotating 90 degrees every time. A new rotation that's 90 degrees to the collective set every time.
My research on that showed that was likely, that's basically quantization. The power tower of I is quantization because you're mapping infinite value into like an affine construction.
Yes. And now we have,
generally speaking,
plus 1/2, plus 1/2, plus 1/2, minus 1/2. They're all real, 1/2 reals, but we have 3 plus and 1 minus. Just like the space-time signature.
Well, also integer spins.
Yep, okay.
So if you're dealing with orbitals and those are dealing with energy, clouds, roughly speaking, they're all broken down into half integer or third integer.
And now we have the next 4, positive 1/2, negative 1/2, negative 1/2, negative 1/2, but these 4 are imaginary, the imaginary parts of the same power towers. That set, first of all, just by itself is phenomenally gorgeous. We have 4 and 4, half of them are real, half of them are imaginary, of the same kind of construction. And on the left-hand sides, It's different arrangements of the Planck boundaries and muon mass and electron mass. This electron mass. The rest of these are all Plancks, I think. Yep. And on the primary or the external action, this one acts 4 pi, 2 pi over G1 squared, which is the fine structure constant. Again, 2 over CQ. CQ is the QRS constant. So we'll get into the specific constants later, but let's take a little pause here. With this, well, no, let me finish the column and then we'll show a little video. Let's keep going down. After this gap, we're no longer halves, and we no longer get reals. It's just now full one imaginary part of the imaginary power tower, all the way down. All the rest of those, the same thing. Okay, so maybe you're unfamiliar with some of these constants, the atomic momentum, atomic unit momentum, right, or the atomic unit velocity, or these different constants. But the point is, there's constants of nature that have this symmetric relationship when we pull them apart into their hyperbolic partition construction. A beautiful pattern between 1/8 of all the constants there are pops up right here. And as you were noting, it's I to the I to the I, the rotation inside of itself over and over and over. Let's look at what the gamma function looks like. All right, so we coded up not just the surface plot of the gamma function. Oops. Full, there we go. But this is the phase plot of the gamma function, okay? And now I want you to try to develop an intuition of what the I to the I construction of all of those relationships are doing from perhaps something you will see here. So all this is the phase plot of the gamma functions, no more complex than that, but we've zoomed way out, so the range that we're looking at is big, and we're gonna zoom in. That's all we're doing is zooming in. We're not changing the function as we do. It's the same function, but we just zoom in. First, it looks like noise, right? And then, oh, I'm seeing a lot of structure, a lot of, and things are flipping around.
Whoa. Pretty trippy.
Pretty trippy. My intuition, there's a lot of parsing here, is that the I to the I power tower structure is directly related to what we're seeing here. The gamma function, of course, and the zeta function are directly related, are hyperbolic structure.
The thing I called the stingray before, which we've seen, which just passed out, that black, or that square, it actually looks like the distribution of the Juz, like the real imaginary.
Well, let me go back and see what you mean. Okay.
It looked like
no, I saw what you said. There was
like,
a moment
when we
there.
zoom in, it becomes extremely simple now and modular.
Yeah.
Right? Okay, these white lines are called branch cuts. So it's where the modular form, where you don't cross that line in the modular form. So you could actually cut it there and fit it together to form a geometry. All right, let's go back. Let's see, where was the thing you said?
So what you'll notice, if I can stand up real quick,
yeah,
is eventually there'll be something that looks like a wedge. It starts to form through all this, and it's distinctly a line here and a line here.
Yeah.
And then it has somewhat of a needle and somewhat of a needle. That's what we call branch cuts. But it's starting to form out right now.
I see it. Yep, right there. And it's, yeah.
And so it seems like it's kind of working the same coordinates as your real and your Zeta coordinates.
Now, is this gamma or 1 over gamma?
Oh, I see what you're trying to say.
The kite,
we'd have to go measure the angle and see if that was any connection there.
Yeah.
Great.
That forms a kite, right? The Z's are a kite, and so the kite that forms out of it appears. And so if there's some correlation, that's interesting to see exactly what scale that is, where it shows up too.
Yeah, that's super cool. Okay, so
it might be nothing, of course.
Might be, but it's worth checking. All right, so where we're at right now is trying to, in the goal of trying to interpret all the constants of nature that express themselves in terms of the hyperbolic partitioning structure, right? We're trying to see how to fit together each one of these expressions. Where do they play their role in the hyperbolic structure so that we can actually build a model, maybe not to scale exactly, but in a computer we can build the model, and so we could zoom in and look at the actual quantized boundaries between each of these structures being formed. The part that we're missing in the drawing right now that we haven't put in there. We want to get that from the way that all these constants fit together, right? We're going to take these clues once we finish settling on, yeah, that's the best representation for the set, that's the best we can find. We're still arguing over our last few details there, but once we're there, the next stage is literally to code that structure internally in a computer. So then we can color code and look and zoom in on each one and say, look, this is why the speed of light is what it is. Look, it's this boundary intersecting with this boundary. Here's the shape of the manifold that's following this. We're going to have a lot more access to the structure of reality when we have a picture for it. Now note, all of those details are completely absent at this point in history. The picture of the modular structure of a projection, a hyperbolic projection, is not to be found. In fact, we find the conic structure in math. We find all these individual pieces relevant all over in math, but we don't have a picture that puts them all together as this is what a minimal universe would look like. This is the structure and the internal boundaries, and this is why it has all these different expressions built in. Note what we're saying is, once we have a hyperbolic space, we have a scale picked for a hyperbolic structure, and we have the modular quantization, the quantum bits for each of those scale, all those boundaries that are being put in there. We break them up into their individual pieces. Then we can put together all of the pieces that twist against themselves to keep the whole projection going. We can put together a literal geometric picture of every expression we call a constant of nature, a fixed feature in the minimal arena, or this minimal hyperbolic construction. Why is it this scale that works? That's the scale that, if you invert the whole thing and put yourself on the inside of the boundaries, is matched to the hyperbolic figure 8 knot. That's the story we're at so far from the things that have popped out in the math, right? So literally the minimal manifold gets formed, and put yourself outside of that structure and look about how all the rest of the universe is dancing because of what the minimal manifold is doing. We get this external expression. So the internal one, the one that makes the manifold the smallest possible manifold, or the hyperbolic figure 8 knot, is what the time boundary is doing. That's why it's not present in this picture. You would have to invert this whole picture completely, and then you would see the hyperbolic figure 8 knot. That's the time limit. That's the time construction responsible for all the external expressions. All 4 of these different boundaries relate directly to the time boundary.
It's possible that the point temperature, in essence, is in some way related to, I don't know, conceptually like a black hole, where it's like the information limit.
There is a
It should be, yes, exactly.
It
definitely should be. In fact, so where we're going to go past this, so we get this finished, ironed out, to get all the last details here. We code the construction internally. We get pictures of how these boundaries look, but then we should be able to make sense of chemistry.
So like if you focus,
in a much richer way than we currently make sense of chemistry, right? This whole system, most simply constructed, would be this, but its quantized version. And that would be just representing the simplest universe there is, which is a helium atom. A helium atom is not just this small little thing with the mass part of the boundary, it's also got the charge boundary and the space boundary and so on, right? It's got this whole large hypersphere that's being balanced under logic. Now, what happens if you want to get a carbon atom? You want to get something other than helium? You got to take the internal parts and twist them up along one of the existing boundaries in another loop. There's different directions to loop up though, right? This is also got modular written all over it, right? What do I mean? We've got a repeating structure of one kind that takes you this way, of another kind that takes you this way, that puts together all the possible chemicals in the periodic table of elements. And there's many different tables you could put together where this one's going count up of the electrons, right? You could count up different ways to get different expressions. But the point is there's a pattern between all this that needs to be revealed. There's some geometry responsible for this pattern.
It's worth noting that the bottom blue one gets inserted so that it's not extremely
long. Really, we should cut right here and take these two and put them way over to the left, and then put these in there.
Weird things that are seldom seen in our...
It always confused me. I'm like, what is this up here?
What are the features here if we talk about the rows? The first row has 2. The next row has 8, and this row has 8. So 2 of them with 8s, and then these two have 18, and these two have 32.
Oh,
that's quite suggestive already, isn't it? I mean, if you have a modular structure and you wrap up once more in the 8 direction, you're going to be moving this way. If you started here, then you're moving that way. If you were at this one, then you wrapped up another in the 8 direction. You go that way, you become this atom that has an extra loop in mass than this one had. And this one would be looping up in the 18. Which one has 18?
charge.
The charge boundary. And why would there be 2?
Double cover.
Yeah, and positive and negative. You could loop up this way or loop up that way, right? So we have 2 rows of 8, 2 ways to loop in the mass direction, 2 rows of 18, 2 ways to loop in the charge direction, and 32 rows, or 2 rows of 32, which are in the temperature. So looping dance between temperature, mass, and charge determines whether you're at helium or whether you're at germanium or any other one, right? The number of loops so the simplest construction would end up being stable. This is the double cover of that. So I guess you could think of the single cover this, but you're not really a complete system until you've described the double cover. So the simplest stable system is helium. If you want to wrap it up and make it more complex, then you can make a heavier atom. But you see, we're going to be able to make sense of that pictorially when we're done with this structure. When we can logically fit together all the actions in the minimal projected universe, then we're going to be able to say, this is what the difference between this atom and this atom is. We could visually see how it wraps up differently and why those things have different properties, therefore. That's going to be fantastic.
Did you want to show the video?
Of?
Periodic table? Or just the
correct
version?
No, it's not good enough yet.
Yeah.
I forgot even about that. I haven't worked on it in so long. I've been doing these other things. But yeah.
I only published it and shared it with Jen just because she has the quantum periodic table she's been developing.
Yeah.
As soon as you brought out that, using that domino tile, I'm like, I feel like I've seen this before.
You know what? I have a new insight now. We should try to do the same structure we were doing on the cones and quantizing it, but see if we can try to do the same thing with the 120 cells. So it's not exactly this, but it does the wrap up internal parts. Right? Let's see if we can. I mean, I don't know that that's the right way to go, but it's worth investigating, and it's really suggestive already.
I may actually have an idea because we're up to 118. If we have confidence in 118, I think I know where the 2 others may go. Just speculation.
Cool. The thing is, I wanted to give a very overview of where we were at. So to give a.
I have a question.
Yeah, go ahead.
So actions. So if we're going back to that universal boundary condition.
The binomial factorization.
Yeah.
Okay.
UBF. So A is an exterior action. B would be the exterior boundary condition.
Boundaries involved in that action, yep.
So essentially one is the kinetic component and one is the limiting component. If it was a reaction, or you looked at it like a reaction.
Yeah. Imagine if you have one boundary equally balancing against another boundary, then you would expect that the coefficient front would be 1.
Or could you?
But if the way they fit together is to make a circle, you expect the coefficient to be 2 pi.
Would it be possible to categorically reduce that to a domain and codomain relationship?
Probably.
Interesting to see.
There's going to be lots of logical.
There's going to be a lot of
analysis.
Yeah.
It'd be interesting to see if that holds.
Yeah. What I really want to emphasize on is we have a story now for a hyperbolic structure that has exact partition constraints, and the partial sets of those partition constraints give us a way to then tease apart the information of every single constant of nature in a way that a pattern popped up, an undeniable pattern popped up. We're peering in and seeing something that no one's seen before about reality. And we're coming up with a simple way of getting to peer in, right? It's the same prescription every single time, a 2-piece construction, a 2-part outside and inside construction. It can have more than one boundary in it. But every single time, those parts have to fit to this logic, to this one hyperbolic balance.
Just shout out to that. I mean, he's gone through 288 constants of nature at least twice now, probably going on like multiple times. I'm not sure if there's another person on the planet that spent that much time looking at all this entire set of constants. So
not even the guys at NIST. Not even the guys at NIST, bro. And men and women.
All the folks there, but that was really good.
Well, hopefully it feels like to me, like I keep doing it because it's paying off, right? I mean, the ultimate goal is to make sense of these mysteries. And if we have one constructive way to make sense of all of them at the same time, that's far more confidence than just say decoding, here's a way to get to one of the constants. If you have the whole set, that's a lot more information, and more importantly, it's relatable. The coherentness of the system pops out then.
It's a new way, perspective of looking at things. Great job.
All right, so that's our project. I hope the project makes sense to those that are interested in trying to participate. I mean, you should be able to do this all on your own at home if you want to, right? If you're a shy person and don't want to directly talk to people at the physics monastery, you still have a route now to try to tease apart by yourself the constants of nature, to make sense of what they're telling you this action and this rule means, right? And the whole set, which is fantastic. So I hope I've laid it out clearly enough that if you disagree on something, you can then take that route and take what your different opinion is and check and try to make more sense of things. We haven't finished yet, so we don't know if we're right? But we have a very small set of things left that haven't fit into this. I think 5 or 6, right? There's 5 or 6 constants that aren't currently in this poster, not being shown. They're missing. And if you count up, there's either 5 or 6 holes. There's the right number of holes left. Just I've kept them off so I could show the legend. In fact, let's look real quick at the legend. Legends are very important in maps. So our legend has the modular constructions of the bases, the 5 Planck constants. We start out with that. We have red n is just equal to 5. It's referencing the fact that there are 5 bases. And remember, in our structure, we're double covering the 5 bases. We're using those actions to invertibly create the whole balanced logic. So if you're double covering the 5, you're going to have a base of 10, right? Double covering 5, you have a base 10, which is why these numbers reveal patterns in base 10. It's not because we have 10 fingers. We're not picking it because that's our favorite and familiar one. It's because the basic logic has 5 bases that are double covering in the inverted construction.
We may actually have 5 fingers though for the same reason.
We might, yeah. But that's not the reason. That's not the reason we're picking this. Just to be clear.
Exactly,
yeah.
Exactly. The logic may have caused evolution to pick that.
Yeah. It may be.
Form to,
And blue B, it's blue and bolded just to make it easier to see. Okay, but it's just the number 7, and it's representing the break and scale symmetry when you have any modular construction, when you get something to go around in a circle. We'll do it in blue. We get something to go around in a circle, whatever size that circle is. Once we've formed that circle, if you want to build larger scale things from whatever's making that circle, from those circles, then you have to do it by adding more of these circles. And if they're all the same size, 1, 2, 3, 4, 5, I didn't really draw them all that well, of course, but this new collection of circles has 1, 2, 3, 4, 5, 6 on the outside and 1. So the second scale of construction, once you're able to make things from things that'll persist, it multiplies by 7. So the way you go out in scale in this construction has a first step of, or break in scale symmetry of 7. That's why that number's there. Also, it's highlighted just to make it easier to pop out from my brain. The j's, which reference our hyperbolic partition construction, right? And then we have a bunch of our hyperbolic fundamental constants. The Giesking constant, the figure 8 knot hyperbolic volume, the Catalan constant, or Catalan's constant, the domino tiling constant, the dimmer constant. Hopefully these make the hair on the back tingle when you have these things referenced. If you've studied them all, you're like, wow, this is a very, very beautiful hyperbolic set. We have the infinite power tower of I, which ends up being a 2-dimensional number here, right? The position you spiral into in the plane. And of course, I is just 0 and 1 in the I direction. But we also have the imaginary golden ratio. We have pi and its cousin pup, the universal parabolic constant. The arc length of the unitary lemniscate, let's draw a little bit for that. We have a unitary lemniscate like this. This goes to 0. 0 in the middle, and this is 1 here. Okay, it goes to 1 and it goes to -1. So just the unitary lemniscate scaled to 1, so unitary, right, has an arc length. An actual, if you put down a rope and try to then straighten it out afterwards, how long is that length? The arc length of that is the symbol S, just the arc length of the unitary lemniscate. The next constants that follow, the lemniscate constant, the first lemniscate constant, and the second lemniscate constant, these are all directly related. We got half, or the length of one petal, so S over 2 equals the lemniscate constant. Then you can take S over 4, so just take one of these, 1/4 of the length, and that's the first lemniscate constant, which is, by the way, the same thing as L over 2, right? So very simple. You can see they're all in the same picture there, but they're lemniscate construction constants. The unitary one. Unitary stuff is very important here. Then L2 is pi over S. L2, the second lemniscate constant, is pi over s. All right. The ubiquitous constant is actually quite related to the same things, and the Gauss's constant. And then we have two very famous constants for splitting. In fact, it's in the logic of the Mandelbrot set, right? Or alpha Feigenbaum constant and delta Feigenbaum constant. I've listed the digits out to 15. We care about to 14, so they'll give us error. Bifurcation logic in the alpha Feigenbaum and delta Feigenbaum, but also in the QRS and the associated QRS constant. So these are four logically bound bifurcation constants, right? The bifurcations in math, not in any particular small system, in math. Then we have more hyperbolic numbers, E. You might say the most hyperbolic number in a sense. It's like the base of hyperbolic. And then I is the iterated exponential constant. It's e to the 1 over e, I believe. And then the Euler-Mascheroni constant we talked about before, the non-trivial zero of the logarithmic integral. It goes through 0, 0, goes way down to infinity, and then comes back up and pierces the x-axis at 1 second spot, another 0. And that's this one. The Dotty number, you've been talking about the Dotty number lately, right? It's built into the limits of hyperbolic construction, right?
If you iterate cosine repeatedly, you eventually, no matter what number you start with,
you end up there.
And then same thing with sine goes to 0 if you iterate it repeatedly. Eventually, it doesn't matter what number you start with, you get to 0. You can't come back from 0 once you get to 0. And then it's worth mentioning that the cosine of the Dotty number is the Dotty number. It's obvious.
It's the fixed point of the cosine, yeah.
But, you know.
Yeah. All right, we got the smallest positive root of the tank function. We have the real fixed point of the hyperbolic cotangent, the Laplace limit. These are all the built-in limits to hyperbolic things.
Besides that, the fact that these are a bunch of numbers, like what could they read? What is that? What could that do? Yeah. Well, here's what it could
do. They all have logical meaning.
Yeah, you have a
They're not just a random string of digits. They tell us something about logic and geometry. You see this lambda peak here?
Yep.
Lambda peak is, where'd it go? The peak wavelength of radiation. And here's something really cool. It's defined as x times e to the x over 1 minus e to the x equals 5. This x that solves that equation is the peak wavelength of radiation found in the constants of nature.
Yeah, that's a very crucial thing.
Cool. All right. Omega 1 and omega 2, these are the internal periodic frequencies of the gamma function. Okay, and the gamma function breaks up in terms of lemniscates, right? It's very related to lemniscates and circles. The first non-trivial 0 of the zeta function, zeta of 2, zeta of 3, the Sierpinski constant, Landau-Ramanujan constant, Madelung constant. These are all number theoretic important central things.
And the gamma itself being kind of obviously an extension into the non-integers of the factorial.
Yep.
So
exactly.
Permutation.
Exactly.
And zeta, right? Zeta is a dimensionally expanded gamma.
It's like a double copy of the gamma with offset limits. Yeah. We also have a bunch of golden ratio related things or continued fractions. So Ramanujan's first continued fraction, the continued fraction constant, the golden ratio, the Paris constant, which tells you the rate at which the continued fraction form approaches the constant, the rabbit constant. These are all related to the golden ratio, right? The Khinchin harmonic mean and the Khinchin mean of order -6. And then we have a special temperature that plays a role other than the Planck temperature. We call it T0 or 273.15000000. We mean that exact, right? And it's the freezing point of water. And then also 1 Kelvin is an important one. Two other pressures, the 100 kilopascals and 101.325 kilopascals, show up in the constants of nature as important structural components, so they're in there. And then we have the base units, of course, but we have derived units. What are derived units? The system's breaking up into different structures, and collections of those structures then do things too. The derived units are the collection structures. You can tell how many we collect.
I was also surprised that when I was going through it that I didn't see more Pascal overall. It's common in.
I've taken it out
Yeah.
in dimensional form. So I could go rewrite the collection of dimensions that make a Pascal and write it as a Pascal, but instead I tend to break it into meters and seconds and so on, so I can see that relationship. But you could go put it back in as Pascals for sure.
Well, one thing that might be worth doing is to specially flag the ones that were Pascals at some point, because they have pressure, so that's a group. Everything that had to be collected under.
In fact, this is what I want to do on the website.
Yeah.
I want to have not just this pattern of all these things available, but I'd like to make it so we could have them grouped in many different ways and just click buttons that take you to that grouping. And so
I'll go through this every single one, and I'll look to see on Codata what was expressed in Pascals, and then I'll make the list of all the ones that were originally in Pascals.
I can give you the list of the actual printout of all of them and just scroll through real quick and check, because they still have it listed as Pascals and listed value.
And then we can basically be like, because there's some of these things that I completely understand and think that's right to limit it to those 5 if you can units. But like I said, collectively in the world, things that are, if something has Newton always or whatever, then it's Hooke's law is always.
In fact, at the very beginning of that chapter where we go through all these values, I want to have a page that gives you all the common units like newtons and pascals and so on, exactly how they translate. So that's easy to reference for people. But so this is where we're at. Again, thanks, John, for the suggestion to change this to J. For those putting it in the computer, maybe your Wolfram Alpha won't read J as a square root of -1, so you can put it as square root of -1 or leave it as I to calculate with. But when we do to think about it, it's easier than saying I to the I, but think of these two things as also being orthogonal to each other. It's more obvious if you say I to the J, then that's just inherent. Okay.
There's also the orthogonal symbol, which is like a thumbtack. You can also use that.
Could use that, yep. Okay, so that's where we're at. This is a phenomenal wall we're approaching here. When we finish arguing out the last few debates, the holes we have left, 5 or 6 pieces, and the next stage is literally to try to interpret how those things are collectively telling us something geometrically and individually. We're going to get the whole thing together and piece by piece, and hopefully we can then start coding it so we can visually access all of these relationships through the scales. We can scale in to this intersection, look what it's doing, scale out to this intersection, what it's doing, so on.
And if anybody's interested in maybe reaching out and maybe they don't feel comfortable doing it publicly, got a little inquiry form on the website, already seeing some interest from different very interesting folks, so feel free to reach out there.
Yeah, and we could use the support of anyone who wants to support this project. I think this project is going to do more in the long run, whether it takes longer than our life or not. When this is completed, this will do more to transform the world we currently live in a very positive way. It's going to give us access to technologies we can't even conceive right now, but those are going to come from an understanding of what reality is, right? So if we can increase the way we think of the world we're in to be more accurate, we'll start seeing the world more accurately, and that kind of elevates us as a species to something that we weren't before. Like now having electricity elevates us to different species than before and conceptually we're different than before that. We can do so many more things in much easier ways than before that. So that's the goal. We're trying to not just understand in a loose way. We're trying to understand in a specific way that allows us to build new machines, to do new actions on purpose, to take advantage of all the things that nature's doing when we want, to use those things to do things for us. So that's going to be a nice, fun stage to transition to. So anybody that's interested in supporting this or joining the effort here, right? Join the effort, try to catch up first with what the goal is in your mind, but using the tool of Wolfram Alpha, which Stephen Wolfram, thank you. That's it. It's my favorite tool. I know I've spent more time on it than any other person alive because I wake up and I get on it and I basically do it till I go to bed, and I only stop to do things like give a lecture. So I'm asking questions on Wolfram Alpha all the time, and it gives you, if you can frame a question mathematically, if you can take anything in the world and anything else in the world and ask a relationship between them, you can ask Wolfram Alpha, is there an interesting closed form that represents this relationship? The more digits you have, the more confident you can be that it's an accurate representation of the thing you're asking. And honestly, almost every question you ask on there, every closed form you look for, you wouldn't have been able to find in a lifetime before. Wouldn't have been able to find. It's just It's so fast how it gives you all the possible closed forms that could satisfy your questions. So the art now is really to get good at asking the questions, because there's a tool out there to give you all the things that satisfy that question. And then you can take the next step. All right, 3 possible things that could satisfy what I asked. That leads to another question. What about this? And you collect more and more interesting questions. And if you're focusing those interesting questions on the actual details of nature we need to make sense of, like the constants of nature and the laws of physics, the rules of physics that we found, the more and more you'll be comfortable with the inherent basis of reality, right? And why they're doing the things that they're doing. So there's more of reality to see. There's far more currently around us, making sense of what structures we're already familiar with. And as we figure it out, we'll be able to manipulate that part of the world, but access it too. So that's the world I hope we all get to take each other to. Anybody wanting to join or support this effort, it's totally welcome. You can do it, hopefully, from what we're providing, the information all on your own, if you like to work more on your own. And if you're interested in working with us on it, then get a hold of Matt, and we'll arrange some time to do it in person. I don't really communicate online because it's far too distracting for these questions. Matt communicates a lot online, so get a hold of him and let us know when you want to come participate.
And I'll have a written, 10, 20, 30 page
instructions for the decoding process. Yeah, that's great.
More stuff to come.
Yep, more stuff to come. This is where we're at, and thanks for carrying it.